Okay, yeah, let us start.
Okay, sure.
So I'll share my screen. Can you see my screen?
Not yet. Sir. Yes, sir.
Okay. Okay, let's continue with the second session. So if you have any questions from the first session, you can ask me now or at the end of this session as well. Either is fine. This session may be slightly shorter. I'm not sure. Let's see. So as I mentioned in the first or the second slide, we look at two aspects. So the first aspect of DO estimation and sparsity, which we saw, was basically sparse algorithms, and how we can apply them to uh, the problem of DO estimation. Some specific examples we saw. Some data set processing, Locata data set, underwater acoustic data set, some simulations, and these things. We focused on one algorithm, so to say, SPL, but other algorithms can also be used. They have so other algorithms from the same compressive sensing uh, background will give more or less similar performance. So you can expect the same. So it's fine if you want to use some other algorithm, which is either faster or slightly better. That is okay. So, but the general observations and conclusions kind of carry on.
Sir, I have a
Uh,
one question from previous session. That's
yeah.
sir, what is the sine theta actually either for azimuth angle or for elevation angle? So the same sine theta will provide both the same equation. The SBL and other method were compared like so in that case so I saw that the azimuth angle estimation is pretty good, but whereas the elevation angle or some more standard deviations are there. So that's what I am asking,
Hmm.
that if it is possible to show some equation on that.
Yeah. So I think there are two questions here. So sine theta, which comes here, that is for a linear array where you can only find one angle. You can call it azimuth elevation, whatever. That is, it doesn't make a difference. It's the angle, with respect to the array axis or the perpendicular to the array axis. You have to choose a convention, and based on that, you will get either sine theta or cos theta, depending on convention. So there's only one angle which you can find. Okay, that's
Okay,
for
sir.
one uniform array, right? Uh, Coming to other, rectangular or other non-linear arrays, which can find more angles, which can find multiple this thing azimuth and elevation, or basically two angular dimensions. So
Okay, sir.
azimuth and elevation are conventions which are used, but they could be any two angle
No, no, sir.
uh,
I am asking
dimensions.
how they jointly estimated, because the sine theta is either for elevation or for azimuth. So, sir, how this plot can be achieved by
Uh,
jointly localizing both of them?
yeah, so for when there are two angles to find, this is not the formula. This formula only works when you're finding one angle.
Yes, sir.
only for one angle. Okay. If you have two angles, the formula changes, and you will have two. So sine theta cos phi, for example, two terms will be there. Two angles will be explicitly there in the formula itself. I have
Okay,
not
sir.
given those formulas, uh,
Okay, sir. I understood. It
but the
may be
formula
in
will.
Cartesian domain, some, or maybe in spherical domain. Right, sir? Hello.
Finding, you will have grid over both the directions, and you will have both. You'll be estimating both of them.
Okay, sir.
That's clear. Okay. Okay. Let me go back to. Let me go to the second part. So in this part, we'll focus on sparse arrays, how they can be used for DOA estimation. So here again, we'll use more or less similar, same algorithms. We can continue to use the same algorithms, maybe with some modification. So algorithm wise, there won't be much discussion, but array, we'll discuss the sparse array part of it. Okay. So what is sparse array, and what is the difference co-array for any given array? So which is which is important. And some examples of sparse arrays, and some again DOA these things. Okay. So sparse arrays, these figures will come to them again. So why and how of sparse arrays, right? So why do we want to use sparse arrays? What is their use? Why not use ULS, right? So all these questions we want to answer. So one of the points to note is in sparse arrays can identify more sources than the number of sensors. So this was not possible with the ULS, with the uniform arrays, uniform linear arrays, or uniform rectangular arrays also. So any uniform geometry you have, using that you can only find, if you have n sensors, you can find n minus up to n minus 1 sources, irrespective of what algorithm you use. You may use the best algorithm in the world, but uniform array will not allow you to find more than n minus 1 sources for a n sensor array, right? That's the limitation of uh, the problem itself. So what sparse arrays does is it realizes that uniform array is actually redundant in some sense, not always. It has advantages, but in sense of finding number of sources or more sources, all these are not needed. We can in fact remove some of them. And so how to remove them, or in fact how to build a sparse array, is again a topic in itself. So some of the specific arrays we look at are co-prime arrays and nested arrays. These have become very popular recently. And the nice thing is they can identify, and you can prove that they can identify more sources than the number of sensors. Right. So that is a very novel thing. Uniform thing, uniform arrays were not allowing you that, right? So if you have shortage of sensors, you may choose to place them smartly in a specific configuration, and still able to locate more sources than what your number of sensors dictate. Okay, so that's one of the main highlights of that. So how this sparse array is able to do this is basically relies on the structure of the covariance matrix. So covariance matrix becomes important here. What are the entries of the covariance matrix? We look at that. and how many degrees of freedom it has. Okay, degrees of freedom is a very generic word. It's used in different contexts, so we'll use it in a certain context. Okay, and point is, carefully designed sparse arrays can increase your degrees of freedom without increasing the number of sensors, and that's what we are doing. Okay, so DO estimation and covariance matrix. So this slide was there in the previous session as well, but what I want to highlight here is that, see, these are all the the main formulas for each of the three algorithms, and other methods will have some similar things. So what you can see is all of these rely centrally on the covariance matrix or the sample covariance matrix rather. SY is the sample covariance matrix. So it comes here, right, in SPL formula. It comes here in CBF formula. In music also it comes indirectly because Bn is obtained by decomposing SY into signal subspace and noise subspace. So SY is decomposed into B signal plus B noise, and the B noise part is what is used here. Okay, so again it's a covariance matrix has a big role to play here. So all the methods depend on covariance matrix, and how the covariance matrix looks for different arrays is important. So let's look at uniform array. So uniform linear array. Okay, so this is again the steering vector from before. So steering vector corresponds to some angle, I'm assuming theta m. So this is the steering vector. Let us write down if it, right. S1 S up to Sn are sensor locations, and I have the covariance matrix, the sample covariance matrix. Okay, this is not the sample. This is the theoretical, right? So theoretical covariance matrix is the expectation of y Hermitian. Okay. So this is equal to this. So if you remember, y is let's say there is only one source. So am into x plus noise. Some m steering vector I'm using. M some direction m. Okay. So what is expectation of y Hermitian there? So statistics, you assume so am x plus n into am x plus n Hermitian. Expectation am x Hermitian, am Hermitian plus noise Hermitian, plus the two other terms, but we'll assume noise and signal, that is n and x, are uncorrelated. So, and they're zero mean, so their expectation is 0. Okay, so this becomes expectation of x Hermitian, so it's single source, so some gamma times am into am Hermitian plus noise is sigma square I. So I've done this for a single source. For the multiple sources, this is general formula. Okay. Everyone follows that? If a multiple source, instead of am into x, I will have summation am xm something. Okay, I will sum over all that. Okay, I can have m here also. Mth source or something. Gamma m. So gamma m is the covariance of this. Okay. Just the summation is missing, right? So RS, is the theoretical covariance matrix. So what are the entries of RS? Right. So sigma square I is a diagonal component, right? So this only has diagonals in it. And if you look at the off diagonal entries of RS, they will be sum of off diagonal entries of AM Hermitian. So what are the entries going to look like for this? See, AM has entries of the form e raised to minus j theta, minus j something, minus j some angle. 2 pi s by lambda into sine theta is whole thing is another angle, right? So so AM into AM Hermitian will have basically entries of the form I have given here. So we'll have entries of the form e raised to j 2 pi by lambda si minus sj sine theta. Okay, right. So this is the right. So all entries of the covariance matrix will have some si minus sj present in it, right? So si minus sj is what? Is the difference between the ith sensor location and the jth sensor location, right? This is the difference. Okay. Si and sj are the sensor positions. Right. For ULA, this has a nice structure. The covariance matrix is Hermitian Toeplitz. It's Toeplitz structure. So you know Toeplitz matrices,
Yes,
right?
sir.
Yeah. So it's basically so you need only one row and one column to specify the Toeplitz matrix, right? And then rest is just diagonally they are similar. So this will happen for the ULA, but for general arrays, it will not be Toeplitz. Okay, it will be complicated. So Toeplitz matrix, let me write Toeplitz matrix some m. So all diagonals will be same. Okay. Okay. So if something is there on the diagonal, first entry it will repeat throughout this thing. Something is there on the left, the diagonal below it, the same entry will repeat, and so on. Okay. So the actual number of entries you need to fill the whole Toeplitz matrix is much less than the full size of the matrix, right? So that's the main thing. Right? And because it's Hermitian Toeplitz, Hermitian means there is symmetry, meaning this component is Hermitian of this thing. So in fact, you only need one row here. So as I said here, it's Hermitian Toeplitz and can be fully reconstructed given its first column. So if you know the first column or the first row, either is fine. You can complete the whole matrix.
So then
Okay.
it will be only transpose, right? Not.
No, it's Hermitian. It's complex conjugacy is also involved. You take complex conjugate also. So
Okay.
Si one in one case it would be Si minus Sj, other would be Sj minus Si. So the sign flips. So e raised to minus it becomes basically. So that's why it's Hermitian Toeplitz.
Thank you, sir.
Right. So this structure it's ULA has. And what is important to note here, this difference of sensor positions appears in this. Okay. So this thing is called difference coarray actually. So right. So difference coarray it's defined as follows. So it's the set of all pairwise differences of the sensor locations, right? So this definition, so you take all Si minus Sj or S1 minus S2, where S1 is, both S1 and S2 are in your sensor location set, right? So this script S, or this I don't know, it's called blackboard S, is the set of all sensor locations. So all differences you take and keep them in a set. Okay. So example is given. V and U will come to it later. Now let's look at ULA. Okay. For simplicity, let's assume all this S1, S2, S3, they're all integers. And you can, that is okay, because you always choose some spacing, some fundamental spacing between the sensors, and then all distances you make them, integer multiples of that. It's okay. You don't have to do that, but that works. So that should be sufficient. Okay. So here,
Sir, is that the sampling is linear or non-linear?
you mean the array the
Means
sensor
some-
coordinates?
Yes, sir. So they are the integer. So the thing is
Hmm.
that the spacing between them are considered as some linear function or some non-linear function, unequal spacing.
For uniform arrays, the spacing is fixed, constant. For sparse arrays, as we'll see, the spacing can change. So sparse arrays are basically that, where the spacing is not constant,
Okay.
changes. Right? So this difference, this thing. So for yeah, I've given an example. Right? So 1 to 4. So you take all pairwise differences. So you'll get 0. You always have, because 1 minus 1 is allowed. So 0 is always there. Something same thing you subtract. Then 1 you get by 2 minus 1. Right? So this example, right? So 1 minus 1 is 0, 2 minus 1 is 1, 4 minus 2 is 2, 4 minus 1 is 3. So 0, 1, 2, 3, all the 4 numbers you get. And then the negative of each of this, because I can also do 1 minus 4, 2 minus 4, 1 is opposite. So I will always get it symmetrically in the negative direction as well. So that is the difference set. Okay. So for 1 to 4, right? So this was the set 1 to 4. I have these numbers. Let me do it for the set 1 to 3. What numbers I get? 1 minus 1, 0. I'll get 2 minus 1 as 1. 3 minus 1 as 2. 0, 1, and 2 I get. I cannot get any other numbers. Can I? Any other difference? I mean, of course, the negatives are also there. So minus 1 will be there and minus 2 will be there. But apart from that, I don't get. So here also minus 1. So I get minus 1, minus 2, minus 3. Right? So this is a ULA. Right? 1 to 3 is a uniform spacing, right? So it's 3 sensor with locations 1, 2, 3. So if I look at the different set, I get 3 numbers, 0, 1, and 2. In fact, any ULA you take, 1, 2, 3 up to n, the only differences you will get is 0, 1, 2 up to n minus 1. Right? Those are the only differences you ever get. Everyone agrees? Everyone can work that out? Okay. 1 to 3 is an example, but if I have 1, 2, 3, 4, I will get differences 0, 1, 2, and 3. If I have 1, 2, 3, 4, 5, I will get 0, 1, 2, 3, 4. And that's all. I cannot get any other differences. So n sensors in a ULA, I get n differences. But now this another example which I took 1 to 4. It has 3 sensors or 3 positions 1 to 3, but I get I'm looking only at the positive part. Okay, negative part is symmetric, so I'm not considering that. I'm looking at the positive or rather non-negative part. Okay, so with 1 to 4, I can construct 4 different things: 0, 1, 2, and 3. Right. So there are more options. More the difference set is bigger here, even though the set S is of same size. 1 to 4 has 3 elements. 1 to 3 has 3 elements. But here the difference set has more elements. Whereas for 1 to 3, the difference set had fewer elements. You see? Okay. So this difference set or the difference coarray set. So this is the important thing here. Difference coarray. So how many entries it has? The difference coarray. That becomes important. Okay. So sparse arrays. So what are sparse arrays? Basically, in our context, is our sensor positions such that the difference coarray has many more elements than the physical array, than the number of elements in the physical array. For the ULA, the physical array and the difference coarray will have exact same number of elements. As I just gave an example of 1 to 3. Right. So physical array means the actual set S, and difference coarray means the set D. Set D is obtained by taking all pairwise differences of elements in the set S. Right. And difference coarray, if I focus only on the positive part or the non-negative part, for ULA, the difference coarray and the physical array have same number of elements. Not exact same elements, but the same number of elements. Whereas for sparse arrays, we design them so that they have more elements than the physical array. So a simple example is this 1 to 4. It has 3 elements in the physical array, but the difference coarray has 4 elements in the non-negative part. Okay, and I can make this array more complicated. So why this is important is because if you see in the covariance matrix, is basically, it has, for ULA, it has this toplet structure. So this toplet structure is only for ULA. And it just repeats because structure depends on this Si minus Sj. The number of different Si minus Sj you have, the number of distinct elements you have in your covariance matrix. So if the matrix, if the physical array is sparse, the distinct Si minus Sj you will get will be many in number, and the matrix, covariance matrix, will not be toplets as well. Okay, so these are basically degrees of freedom. So or you can say your covariance has more diversity. So the more distinct elements you have, you can then smartly combine them or reorder them to get higher degrees of freedom or to localize more sources. So let's look at some examples of sparse arrays. So coprime array. So the two examples we'll see, coprime and nested, they're both built from uniform arrays only, but by combining two different uniform arrays. So coprime combines two ELAs whose spacing are some d into n1 and some d into n2. n1 and n2 are integers, and the condition is that they should be coprime numbers. So coprime numbers are numbers which do not have any common factors. Okay, so for example 3 and 5, so they need not be prime. So for example 15 and 16 are coprime because they don't have any common factors. right? So N1 and N2 should be co-prime numbers. That's the important part. So you take two ULAs with such spacing, you combine them, you take union of these two, right? So union here. The two. So this is the first ULA, ULA1, and then you take another ULA, ULA2, just union, to combine them, and that becomes your co-primary. ULA1 has basically spacing N2, and it has N1 elements, and ULA2 has spacing N1 and it has this has 2 and 2 minus 1 elements. So there's specific geometry which is recommended here. Why this is recommended, we'll come to it. So for example, if I take N1 is 5 and N2 is 2, D is 1. So D is just some fixed spacing. So it's the integers N1 and N2 which are important. So I'll get these two sets, right? So 0, 2, 4, 6, 8. The first ULA, it's spacing 2. And the second ULA is 5, 10, 15. The spacing is 5. Right? And the union of this is this array. Right? So in this, the figure co-prime array, white means empty space, right? There is no array. And gray or black means there is a sensor there. So gray is used for the first ULA and the black is for the second ULA. Okay. So the sensor positions I've given started from 1. I've shifted this. Okay, I've shifted. Okay, here my set starts from 0, but I've shifted to the right by 1, so that's why it starts from 1. But otherwise, this would be, I think, 0, 2, 4, 5, 6, 8, 10, 15. Okay. This would be the set, right? 0, 2, 4, 6, 8 is there, and 5, 10, 15 is also there, right? Just shift to left and right is not going to change the nature of your array. Sparse array is still going to remain a sparse array. Okay, just the indexing is slightly different here. So this is one example of sparse array. And we can find its difference co-arrays also. We'll come to it later. So take two ULAs and combine them like this. Condition is N1 and N2 should be co-prime numbers. Next is nested array. This is again you take two ULAs and merge them.
Sir, may I ask one question, sir, regarding that co-prime array that you designed? Sir,
Yeah.
it seems that between the 0th sensor and the sensor number 2 that is being written, the D is now the distance is greater than lambda by 2, it seems. So, sir, how we can encounter the spatial aliasing in this case?
No, not necessarily. So D is some. I took it to be 1. It is. Okay, let me go back here. So here I have something like S by lambda into sin theta. So D is no, it would depend on lambda also, right? So this is again, maybe I'm doing shortcut here, but so it's some kind of normalized distance. So D is not actually this T. It's with respect to the lambda already. So I will make sure that the D is lambda by 2 or less. That is okay. That is all. That is possible. Don't have to worry.
Okay.
Yeah. So, but I mean, this issue of spatial aliasing still arises because D is not the spacing between the consecutive sensors. Some sensors have spacing D, some have more than D, right? So
Yes,
10 to 15, there is lot of gap. So yeah, so your point of spatial aliasing still remains. Yeah, that I agree. Right. So it depends now on the methods and how do you use observations from this sparse array, the way you use it decides if you get aliasing or not. If you directly use it, it's likely you will get aliasing. But what we'll do is we'll do some pre-processing before using it.
Yes. Okay, sir.
So next is nested array, again 2 ULAs. One is a very dense ULA with spacing D. It's very simple. So D, 2D, so on up to N1D. So it's first part is this, and then next is N1 plus D, N1 plus 1D, 2N1 plus 1D, and so on up to N2. So again, two parameters N1 and N2, similar to above, but there's no requirement of coprime and all. So if you see here, this is the nested array. So one is a dense array. So this part is called the dense part. Right? So this is like a ULA only. Right? This is like the dense ULA with one spacing, and then there's a black part which is much further apart. Right? So this is the other part, 5, 10, 15. Right? So here, so it's nested, right? So nested in the sense, right? The dense ULA is nesting between, the non-dense ULA, so to say. Right? So the complete dense part comes, and then you have large gaps. Whereas coprime is different. It can have different geometry as long as N1 and N2 are coprime. So it is basically merging together of two ULAs of with this coprime spacing. Spacing between the elements has to be of coprime nature. That's the condition. Okay. So why these two? What is the benefit of these two sparse arrays, and how does the difference array come into it? So if you look at the difference array of this, can we try to list for this coprime array what is the difference, or for this nested, which is easier? Let me see, this 4 plus 3 is 7 sensors. This has 5 plus 3 is 8 sensors. Let me try to list the difference array for this nested array. Okay, so what is the set S here? It's 1, 2, 3, 4, 5, 10, 15. Okay, I want to list the difference set. So I have 0. I will list only the positive part of it. Okay, let me call it D plus. So we'll have 0 always, right? Anything minus the same thing will give me 0. Do I have 1? So we have to find, all possible pairwise differences and see what all numbers we get. Right. So that's the idea of difference coarray. Correct. So do I have 1 here?
It's 1, 2, 3.
1
Yes,
I
sir.
have,
We
right?
have one.
So we have 2, right? So 2 minus 1 is 1, 3 minus 1 is 2, 4 minus 1 will give me 3, 4 also I have, 5 minus 1, 5 I have,
10.
10 minus 5 will give me 5, right? 5 I
Yes.
have,
10.
6 do I have,
7.
10 minus 4 will give me 6, right?
Yes. 6, 7,
6
8.
I have. So 10
7,
minus
8.
3, so 7, 8,
8, 9.
9. 15 minus 5 will give me 10.
15, 15 minus 4,
15
11.
minus 4, 11. Similarly, 12, 13, 14. This is largest minus smallest, 14. That's all, right? It can't be more than this. So I have all numbers from 0 to 14. Right. So the physical array is of size 7, and the difference array has size
29.
15 elements I have, right? 0 to 14. 15 plus there is the negative also, which I am ignoring. The positive part only I am considering. So it is it is about 15 elements. Right? The difference array has many more elements. You can do the same thing here also. Here also, I'll leave it for you to figure out. So this is 0 to 4, 5, 6, 8, 10, 15, and then you find the D plus for this one. Okay, I will leave that for you to work it out. So what we saw in nested is that you get a continuous set of numbers from 0 to 14. In coprime, that may not happen. What you will in fact get is a continuous set of numbers till some point, but after that there will be some gaps. I mean, not continuous. These are contiguous numbers. These are spacing 1. So here also you'll get numbers with spacing 1, but then you'll also get numbers with slightly more spacing. Okay, you can work it out. Okay, so difference array has so many elements, right? Difference core. So now if I were to right, so here, okay, here I've given the example also. So the nested array is the one which we figured out, right? So the difference array has 0 to 14. I am numbering here from 1, so that's why it's different. So it's from 1 to 15, that's all. The same thing, right? So this D plus has 15 elements. So black dot means all those elements are present. Okay, and for coprime, you can work out. You will see you'll have a lot of things. So 1 to 16, or rather 0 to 15, but some of them would be, 2 of them are missing here. Okay, that would happen. It's still okay, still much better than the physical array. So the size of D plus is much bigger than the size of the physical array. Okay, so U plus and V plus are basically, this is more useful for mathematical analysis. U plus is up to what point you have continuous numbers without anything missing in D plus, and V plus is everything filled up from first to the last. Okay, so these are difference co-arrays for the above examples. Right. I don't know. Okay. So now what happens is, if I look at covariance matrix, right? We go up. Yeah, this one, right? It will have entries of the form e raised to j si minus sj into something. Right? So if it's a ULA, I know there are only n distinct si minus sj possible, the positive or the non-zero ones. Sorry, not non-negative ones. Whereas if it is sparse, si minus sj is nothing but the difference co-array, right? So si minus sj will give you a lot more, right? So for the example we took, for a 7 sensor nested array, I will get 15 si minus sj's, or 15 distinct entries in my covariance matrix. It will not be toplets, but it will have 15 distinct entries. So now what I can do is, I can imagine, or I can imagine, or I can consider a virtual array. So this is the physical array. I can consider a virtual array which has 15 elements. For this specific example, let's say 15 elements. If I had a virtual ULA uniform array with 15 elements, what will be the entries of its covariance matrix? It will be Hermitian toplets thing, right? But whatever entries it will have, I am also getting by from this itself, from this sparse array. So what I need is Si minus this distinct Si minus Sj. So if I have this distinct Si minus Sj from the sparse array, I can collect those things and construct a Hermitian Toeplitz covariance matrix corresponding to some virtual ULA with 15 entries. So now basically, now it's like I have a covariance matrix of a much larger array, which does not exist physically. Physically, it's only a 7 sensor array. But I can make a covariance array of 15 dimension, 15 cross 15. If I directly make a covariance matrix, it will be 7 cross 7. But because of the sparse structure, I know my entries are not Toeplitz, so I can select the non-unique ones, sorry, the unique ones, and make them into a 15 by 15 covariance matrix corresponding to some virtual ULA. So that is the main idea. So what we are doing is using this diversity in the difference co-array. And why difference co-array? Because that is the main thing in the covariance matrix. Difference co-array decides which element is distinct and which is not. So I use that fact to construct a new covariance matrix and then use it to, then I can use any of my algorithms, right? Where are they? I have so many algorithms. All they need is SY. So instead of using a direct 7 cross 7 SY, which will not be Toeplitz, I can make a 15 cross 15 Toeplitz SY and then keep other things same and just run it. All these algorithms I can run. So I virtually expanded my array dimension. Physically, I have few sensors, but virtually, because of the certain structure of the covariance matrix, I'm able to virtually expand it from a smaller covariance matrix into a bigger covariance matrix. And now I can do DOA estimation. So now because my virtual array for which I have the covariance matrix has 15 sensors or 15 virtual sensors, I can localize up to one less, that is 14 sources. Whereas I would not have been able to do that earlier because if I had only 7 sensors. So 7 sensors arranged in a ULA and 7 sensors arranged as nested array. Just the position that is changing. Number of sensors, if you keep the same, you would prefer to use nested array because you can make them into a virtual array and use it to find more sources than actual number of sensors. So that is the whole idea. Is that point clear?
Yes, sir.
Okay. Let me know if you have any questions. So then I have I also plotted, Gram matrix. So you're familiar with Gram matrix? Gram matrix is basically a plot of a Hermitian A, I think. So it's called a Gram matrix. It tells you, if there is aliasing in the sensor array or something like that. If you look at the Gram matrix for the above 3 cases, it's for the same example. I've taken a ULA with 8 sensors and then co-prime and nested arrays with 8 and 7 sensors, as in the previous example. So this is, angle, both axes are angle versus angle, and this is is basically correlation between various steering vectors. That's all. That's what is Gram matrix. You find correlation between each combination of steering vectors and plot them. So Okay. So what happens is, compared to ULA, ChroPrime and nested array have a much larger aperture, right? Aperture means the distance between the first and the last sensor. So the larger the aperture, it makes it easier, or it gives higher resolution. Okay, so that is reflected in this gram matrix. So this yellow band, if you see, it's basically, how the nearby these things are correlated. How the nearby steering vectors or angles are correlated. So the thinner it is, the more, the better resolution you will have. So nested and coprime, even with same or fewer sensors, they have much better resolution, because this thing is much sharper than what the ULA can give you. So two advantages. One is that you can find more sources than sensors. Second is the sources which you can find them with higher accuracy. So like two things you are getting by using sparse arrays instead of uniform arrays. Okay. So processing. So then I've applied it to various algorithms to process sparse array data. So you can use CBF, music, and SBL as before. You also have what is called co-array music. So what co-array music does is basically it applies music, but on the on this virtual difference co-array based covariance matrix. So which allows you to resolve more sources than the number of sensors. So co-array music is so as I mentioned, RS is not the covariance matrix is not going to be complete summation for sparse arrays, but you can construct a column vector out of which to make a complete summation RS, which is the virtual, basically corresponding to the virtual. So U plus is this continuous part, right? If you see, U plus is where all the elements are contiguously present. So up to that part, you can consider them to be a virtual ULA. Okay, you are able to hear me?
Yes, sir.
Yes, sir.
Okay. Yeah, thank you. I'll just continue. So you can construct a column vector, right? And then you can get a new covariance matrix RU plus, right, which is of much higher dimension. Right? So the co-array music will work directly on the RU plus instead of RS. So RS would be, for example, in the previous nested array we saw, RS would be 7 cross 7, whereas RU plus would be 15 cross 15. So I have a higher dimensional covariance matrix. You can use this RU plus for SBL as well, or you can directly actually work with RS itself, and SBL will internally take care of it. You don't have to specifically rearrange into RU plus and all this. It will automatically work with these things, and or it will automatically, you can say, or it will utilize the additional degrees of freedom which sparse array has without any special rearrangement, and still be able to find out all the sources. Okay. So any questions so far? Okay. So then I have a bunch of results. So here I am comparing SBL and co-array music. So first three columns are three different array types. So first three columns are all SBL algorithms, and the last column is co-array music. I think co-array music is applied on either co-prime or nested. I forgot one of the sparse arrays. So top row is k equal to 4 sources, second row is 8 sources, and the bottom row is 10 sources. And the number of sensors are 8 for ULA, 8 for co-prime, and 7 for nested. So when there are 4 sources, all of them, SBL, everything, all arrays can find them. K equal to 8 sources, because ULA has 8 sensors, it can find only up to 7 sources. So 8 sources, it does not work. You see, the spectrum which you have got is very poor. It will find some sources, but not all of them. Whereas if I use co-prime array, I can see all the peaks in the correct locations. Right? And similarly for nested. And in fact, I can go one step further. I can have more sources, k equal to 10 sources and 8 sensors. ULA will not work irrespective of the algorithm you use. But if you rearrange the 10 sensors in a co-prime fashion, you see that you can find all, you rearrange the 8 sensors in a co-prime fashion. You see that you can find 10 sources all correctly. In fact, even the nested 7 sensor can be used to find 10 sources. Right? So more sources you're able to identify by this rearranged, this new geometry. So both SBL, the first 3 columns, as well as co-array music are able to do that. So k equal to 8, co-array music works well, but k equal to 10, it's not working as well compared to SBL. So that was just a comparison of SBL and co-array music. So co-array music will still have the resolution similar to music, whereas SBL will have, as we have seen before, it has a better resolution than music. So that fact is still valid here as well. So same thing you can see by changing number of sources. Right? If I slowly increase the number of sources, when does the error start rising? So I am plotting RMSE versus number of sources for 3 different array types at various SNRs. So let me focus as 20 dB SNR, right? This one here. So again, 8 ULA sensors, 8 co-prime, and 7 nested. So as the number of sources hits 7, right here, black is the ULA, right? The ULA has low error up till 7 sources, but then for 8, it suddenly shoots up because it cannot find 8 sources, 8 or more. Okay? Whereas co-prime and nested, they continue to work good up to 11, 12, almost 13, right? So this is 13 sources. The error is a bit higher, but it's still less than 5 degrees, right? So it's still able to find. So this is, I forgot the exact source locations here, but.
Sir, if the sample size can be increased, then the number of sources can be identified. Number of sources identified would be more, right, sir?
What do you mean by sample size? Number of
Sample size means
snapshots, you mean?
the total sample you have taken on the this Twelve matrix, the AH or A, that one. So if we increase the sample, so you are differencing in that case to augment the increase the sample, right, sir? So if we just increase more on the sample size and do the same operation, this fusion of these 3 different sampling, so sir, the performance would be better, or sir, the same will be there?
I didn't fully understand. So do you mean
Sir, the sample
increase the
size
number of sensors?
0, 1, 2, 3 up to 16, or how
So it is a difference core. Yeah.
yes, so the
So
sample size would be more, so the detection would be more. So is it proportional? So that is I am asking.
Yeah, so for all the sensors, ULA or sparse arrays, if we have, see for ULA, if you have more sensors, you can detect more sources, right? If you have 10 sensors, you can find up to 9. If you have 15, you can find up to 14, right? For sparse, for the example I give with either 7 nested or 8 coprime sensors, I can find, for, okay, let's see nested. For 7, I can find the difference core has size 15. So I can definitely find much more than 7 sources. And if I increase the nested further, I can have 8 sensor nested. The difference core size may further increase, and that will allow me to find further more sources. Yeah, that is correct. I hope it's clarified.
Yes, sir. Thank you, sir.
Okay.
I have a doubt that when we are finding the difference, what it means difference in the sensors current or difference between just the index difference or what is the exactly the difference means?
Okay. So here, if you see, so the difference is the pairwise difference between the sensor locations or normalized sensor locations. So they are always integers, and I focus on the positive integers. Okay. So what we are saying is this RS matrix for a sparse array will not be toplets. Okay. Not be Hermitian toplets. So it will have. If it was ULA, it has only distinct elements along a row or a column. That's all. But when it is sparse, you will have distinct elements like this and some other distinct elements in between also, in other parts of this thing also. Okay.
Okay.
So this I will find using empirical covariance matrix. Okay. So this SY I will estimate using SY, sample covariance matrix or empirical covariance matrix. With this, I will make a new covariance matrix RU plus, which basically takes all these orange markers and prepares a Toeplitz matrix with it. And this is Toeplitz, so this will all be same. So this now corresponds to a ULA. This corresponds to some virtual ULA. There's no true ULA like this, but this is a covariance matrix of some virtual ULA, which was obtained by this thing. This is for sparse physical array. Okay, so what I'm going to do is RS is this. So I will compute RS empirically or numerically using sample covariance matrix, that is SY, for the 7x7 array covariance matrix. And I know Si minus Sj, there are many distinct Si minus Sj for sparse arrays, hence there will be many distinct entries in the covariance matrix. That's the idea. The number of different Si minus Sj you have, the number of different elements you get in the RS matrix. But if I want to think of this as a ULA, I can take this distinct Si minus Sj, especially in the contiguous range, right, the U plus range, and I'll put them all together like this. I'll construct this RU plus. Okay, this RS, RU plus. And this RU plus is now a core for a virtual ULA. Sorry, it's a covariance matrix for a virtual ULA. So this I can use for my further processing is what I'm saying.
So with the help of lesser entries in the correlation and covariance, that RS, we can able to generate the ULA kind of RS.
Yeah, with lesser or fewer physical array entries, I can get more distinct differences. The difference core is larger still because I have placed my sensors in a better way, and that helps me to translate that into a ULA kind of thing with much more entries than what the physical array allowed. And this can now be used for your regular processing.
We can able to
Estimate more sources if you want to.
okay.
Okay.
Can this be used? Can this be used to for recovery process also, detection process?
Recovery means DOA estimation.
Not detection process.
Deduction of what?
Support direction.
Yeah, support deduction is same as DOA estimation for us. Support tells us what are the DOS, so you can use it. Yes, you can. So in your SBL, you can use RU plus instead of SY here. And SBL is basically a support deduction method, right?
Yes.
Yeah. Okay. Then so this was SBL compared to music, and this number of sources, as you can see, like I can find up to 13 sources, even 14 is okay. So you can find much more sources basically. That's the idea. Even though my physical array is not so big. Of course, it will suffer with SNR. That is bound to happen. Lower SNR will degrade performance, the error performance. It's 20 dB, this is 10, and this is 0 dB. Right? Okay. Next, some experimental results. So this was the same, acoustic underwater acoustic experimental data, which I showed you earlier. Right? I showed you the. Let me go back. The last slide. Yeah, this one, right? So here I showed you the whole, 0 to 20, 30 minutes of data processing using various algorithms, right? This has, I think, 16 sensors are used here, something like that. So now I'll focus on this SBL part, and I will process. So instead of using all 16, so this was processed using 16 or 64. I will come to it. All the it was a ULA, so all the sensors in the ULA were used. Uniform array. Now what I will do is I will process only some of those sensors, so it becomes a sparse array. Okay, yeah, so it's a 16 element array, right? So it has 16 sensors, the ULA, full ULA. So what I do is take various subset of this. So ULA1, I call it is the first 8 sensors. ULA2 is every alternate sensor actually. So the spacing has doubled. When you double the spacing, aliasing and all may arise. Then I've used coprime and nested listings. So I think, yeah, again, these nested and coprime indices are same as what we saw in the example before. The 1, 2, 3, 4, 5, 10, 15 was the nested example we saw, right? So this 16 element is the full array, full ULA. And I process the same data. So I'm focusing on only the half of it, 15 to 30 minutes of the data. But I'm processing using different arrays. So full ULA has 16 sensors, coprime has 8, nested has 7, ULA 1 has 8, ULA 2 has 8. Okay. So I want to basically reduce the number of sensors. See, when I'm deploying a ship with huge sensor attached to it, I would like to use fewer sensors if possible. So we are investigating that possibility. How to deploy this sensor, what positions they should be in and so on. Okay, so the full ULA gives you the the best result. See, even if it is ULA, if you have more sensors, it will do better than coprime and nested. That's possible, because if you have more sensors, it means you have uh, SNR will be higher. Your overall noise you can suppress better if you have more more sensor observations. So that is still there. So what we want to see is, can I reduce this 16 to 8 or a fewer number of sensors while still retaining the performance of the full array. So that's what we're investigating. So if you look at the ULA1 part, this part, there is a lot of blurring happening in this, 25 to 30 minutes region. And that's because what is ULA1? ULA1 is the first half of the ULA, right? So it means I'm using only half the sensors, but they are still in a ULA form. And that, so small, half the array size means my resolution will come down to half immediately. I cannot resolve nearby sources. And that's what is clearly visible in when you compare full ULA to ULA1. Okay. Whereas if you see coprime and nested array results, they are pretty, to zoom in, they are kind of very similar to what the full ULA was giving. So I am able to reduce the number of sensors and still process, it's actual acoustic sensor data from, from ship experiments. So it's actual experimental data processing, which and its work seem to work pretty well. Here ULA2 also seems to work, though there are some missing angles. So ULA2 was the array with alternate sensors. So it's ULA, but it has large aperture, so it will be able to resolve better. But this will have more aliasing because you have doubled the spacing basically. So it will have more aliasing compared to ULA1. So that part is not clearly visible here, but there are definitely some portions which are missing in ULA2 results. Okay. So is this figure clear? So let us look at, so this red vertical line,
Sir,
is where,
actually, I have one thinking on that. Sir, as we are differentiating, we are actually putting a dimension, one dimension less, or something, or n minus one dimension less. So, is that maybe the reason for second half not coming properly? Differentiating or adding kind of is kind of
where
adding
are we
some dimension.
differentiating?
Sir, I am saying that the from 24 to 30, this region is getting blurred because of the differentiating or some other reason?
No, this is getting blurred because the sources are coming closer and closer. The angles are closer here.
Okay, sir.
Directions are closer, so it's you cannot resolve it anymore.
Okay, sir.
Right. So the vertical axis is the direction of arrival, right? So the angles are getting closer and closer. So maybe they are separated by 10 degree or less. And when there are many sources present in such proximity, and algorithms will suffer. So that is what is happening here. And of course, the ULA is half the size, so its aperture is less, so its resolution is automatically reduced. Okay.
Thank you, sir. Yes, sir.
And a cross section of all these things is plotted in the next figure. So for comparison, so this is the traditional, horizontal is angle and vertical is the power spectrum. So this tells us in which directions the angles are present. So full ULA can identify for up to 7 angles, right? In this 20 between 20 and 25, this red line wherever it is, I think 22.5 minutes or something. It's able to find all 7 up to 7 sources, not sources but 7 directions of arrivals. Coprime is able to find 6 nested, or nested also finds 7. ULA1, you see, it's because of lower resolution, it has broader peaks, so its peaks are starting to merge or miss. That's what I was trying to say. ULA2 also kinds of works, but yeah, in this case ULA2 also works. Maybe it has some more peaks. I don't know if it's a true or false peak, so that we don't know, but it's able to find. But it could be a earliest peak as well, right? Because we know ULA2 will have a little more aliasing than full ULA. So it could possibly be aliasing. I'm not sure. Okay. So these were all 1D DOA estimation. So same thing, we can have 1D sparse arrays and 1D direction estimation. We can also have 2D sparse arrays and find 2D angles. It's very similar extension. So I'm not mentioning any theory here, but I'm just going to discuss some results which we got from an experimental analysis. So so you can have co-prime arrays and nested arrays in 2D, which will look something like this, right? So so red and blue are the two ULAs which have been merged, right? If you look at the top left as the co-prime 2D co-prime array, so red is one ULA and blue is another ULA. Their spacings are related in a co-prime manner. Similarly, nested, if you see, it will have a dense part and then it will have a spread out part, the two arrays. These are sensor locations. So these are 2D sensor locations on a grid. The bottom, the bottom left and bottom right are the 2D difference co-arrays these will generate. You can see there is almost a huge number of points which it covers. So, I mean, this you can say these are the virtual arrays. The bottom panels are the virtual arrays. The physical arrays, they have fewer sensors, I think here 25 or something. Whereas the virtual array will have a large number of sensors and it's nice contiguous region. So this is very useful, or this is basically similar to what we saw for 1D. So my 1D figure, if I go back to, yeah, so this is my 1D is a physical array and the difference co-array. Same thing I'm showing for a 2D case here. So the physical array is top row and the difference co-array is the bottom row. So we did actual experiments, or my collaborators did, and I did the data processing. So you have I think 6 by 10 sensor array. So there are 60 sensors. So if these figures are visible, this is a sensor array setup. So in a grid, it is nicely arranged, So we start with a rectangular array, and then what we do is we process only some subset of it, so it becomes a sparse array. So experiment wise, it's easier to collect all the URA, uniform array data, and then you can process it using some subset of it. Okay. This is the actual experimental setup. I will not go much into the setup. So some of the results which we have seen. Yeah, so this is the subsampling, right? So the top row is that from that 60 sensor array, I made a physical array of 10 sensors, a coprime array of 6 or 7 sensors, a nested array of 5, 6 sensors. And then the second row is the 2D array, right? So 2D physical array. And the third row is the difference array which you can make. So some examples or some configurations of arrays, physical and virtual, which we actually implemented, processed. So what are the results we got? So these are uniform results, uniform sensors. I have 5, 6, and 7 sources. Each column here has different number of sources. So 10 sensors, so I can comfortably find 7 sources. On the left figure and the right figure, I have 60 sensors and I'm finding up to 12 sources. I can easily find them. Of course, music and SBL work much better. CBF, because of its poor resolution, it's not able to find all of them. Right, so top row is CBF, second row is music, bottom row is SBL. You can clearly see, SBL has very sharp estimates. Let's look at this one, right? So circle is the true location of the source, and these dots are basically estimates you get. So it works pretty well here. Even music, if you see for 12 sources, it does have some, broad peaks, broad regions where it's hard to distinguish sometimes. Whereas SBL is much cleaner that way. Then from uniform, we went to coprime and nested arrays. So coprime 6 sensors, nested 5 sensors. And you can see I can find up to 7 sources also using 6 sensors. Right, so SBL will work. Music and CBF will not work. This plain music, I'm not applying core music here. If I use core music, it will, I think it will work, but we have not applied that here. This is just simple music. And yeah, same observation for nested array as well. And then it's probably one of the final slides. Results for 2D coprime and nested arrays. Again, I'm increasing number of sensors, but number of sources by keeping sensors fixed. And let's see. So 12 sensors and 12 sources I can find using coprime and SBL. The bottom column, bottom row. CBF and music, they cannot work in these things. So this is the ability of compressive sensing algorithms, high resolution ability. Yeah, and so another way to compare resolution is how if you can distinguish. So here I have 2 sources. I forgot how this. I need to check 1 second. I forgot how separated they are. I think 5 or 9 degrees separation they have, the 2 sources, and I'm applying various algorithms and various arrays. So you can see as a function of SNR, right? So coprime and nested, right? So they all have Okay, URA has 60 sensors, really high. Coprime and nested have 12 sensors. It's like 1/5 of the number of sensors. But if I look at the plots, they are very similar for all three arrays. Right, the resolution accuracy is very similar. At least from SNR minus 10 dB and higher, they are almost matching. Right. So what this means is, I can effectively use coprime or nested sensors for having high resolution instead of using 5 times more sensors as in URA. So by simple smart rearrangement of sensor positions, I can get same resolution accuracy with in this example 1/5 the number of sensors. So it's a very economical way of collecting data, especially when if your sensors are very expensive, or if you want to deploy them in scenarios where each sensor is taking each sensor takes a lot of effort and all these things. This kind of processing becomes very handy. Okay, so that's the I think last technical slide I have. Any questions?
Yes, sir. Sir, I have
Yeah.
one question, sir. Sir, sir, I am also working in DO estimation area, sir. So
Hmm.
I came across this term called non-circular signal. Non-circular signal where they takes
Hmm.
the summary, sir. Actually, sir, my question is on simulation side.
Hmm.
Simulation side, sir. I give our the signal as complex normal distribution, x by root 2 plus I by root 2. The noise is modeled as random 1 by root 2 into random plus I into 1 by root 2 into random. I give this command for the circular signal. Till now I modeled. So sir, what
Mhm.
should I give the command for this non-circular signal, sir, from the
Uh,
simulation point of view?
by circular, you mean complex Gaussian circular noise, or?
Sir, complex normal distribution I gave sir for this
Hmm.
circular signal, that is x plus iy by root 2 x plus.
Okay.
This is the circular signal I considered actually. This is the and I calculated the measurements and constructed the covariance matrix. From there,
Hmm.
from their applied algorithm, I got the results.
Hmm.
This is the first circular signals. Sir, what should be the distribution of, sir? I want to know for circular, non-circular. What should I give, sir? X plus I. What is the distribution, sir? Sir, for circle.
I'm not fully understanding. So I'm assuming it's about complex noise and how to generate that.
Yes, sir. What should be the distribution? Yes, sir. For non-circular signals.
So I'm not familiar with the circular and non-circular terminology.
Okay.
Uh,
Sir,
I don't know.
sir, it exploits second order not non-circularity properties. Mathematically, expectation of x into x transpose equal to 0, they are considered circular signals, sir, generally. If it's not equal to 0, then they are considered non-circular signals. Till now, I am giving circular signals as the noise. The noise is modeled as complex normals. 1
Okay.
by root 2 into
Hmm.
random plus I into 1 by root 2 into random. I gave that command. I generated the measurements and generated the covariance matrix, and I got the results from.
Hmm.
So,
Okay.
sir, now second order non-circular signals. They said,
Hmm.
sir, in papers in literature, they said that you should change the distribution somewhat. Sir,
Hmm.
I don't know what to change. That's why sir, if you know, if you can help me, that's what I'm asking, sir. If you know,
Okay.
that's second.
I mean, so generating a signal with different distributions, so that should be straightforward, I think. So you just
Sir, sir, they didn't mention clearly in any of the papers, sir. That's why I'm asking if you
hmm.
have any. Please help me, sir.
uh,
If you know
yeah,
something about
yeah. Right now I don't know, but yeah, you can write to me or something, and then I can reply. I need to see the context and then I can probably help you. Right now, I am not getting the full context.
Okay, sir. Sir, can I send a paper to you, sir? Can I email that
Yeah,
paper,
you
sir?
can email with the paper and the query and probably highlight which equation you mean. I
Okay,
might be
okay.
able to help then.
Okay, sir. Because I'm working from 2 months, sir, I'm not getting clearly, sir. What is that? What should I give working? So
Okay.
that's why, sir.
Hmm.
Okay, sir. Thank you very much. Thank you.
Okay.
One thing I can add in that the non-circular signal is kind of a sine of sine theta. This kind of signals are more non-circular.
Hmm.
So in that case, the sine theta is circular, but sine of sine theta is non-circular. So
No, in MATLAB, what kind of command I should give, or what kind of distribution I should? Tamish, you said no, Tamish.
So here, like Santosh sir is defined that here actually is for the azimuth and range. So for the distribution, if you want to change, you can change the instead of e to the power j omega t. So it will be like e to the power same uh, some other function.
Okay. Yeah. So just write to me and I
That's
will
what
try
I can
to
say.
get back to you. Yeah.
Sir, okay, sir. Thank you very much, sir. Santosh, sir.
Yeah.
Thank you very much.
Yeah. Any other questions either from the first part or second part? So I think I have, yeah, last thing is, yeah, just, yeah, I mean, all this work I have not done alone, of course. I have had a lot of uh, collaborations over, past, I think 5-6 years, which has resulted in some of the work that I've presented. So these are collaborators from various places I worked with. And yeah, so some references for the topics that I've covered in the second part of the talk. So, yeah, so slides wise, I finish here. Yeah. Yeah, if any questions for from first part or second part, please you can ask me now.
Sir, the time the DOA estimation came from three different angles till now I see, like time, frequency, and angle. So this angle actually is concepts nicely provided by this previous talk. But sir, this presentation completes the DSP sense in that case. So sir, I want to ask that, sir, the grid you are mentioning that how sine theta is complete the grid. Is there any r sine theta kind of term would be there? So this r equal to this e to the power the s I minus sj absolute value. So this is the kind of understanding, sir, I got. Sir, am I wrong or sir am I right, sir?
Um, we go to the formula. I'm not sure I understand. One second. Let me open expressions. Yeah,
The
here.
sine
Yeah.
theta term.
So,
The sine theta term.
uh,
This
yeah.
this sine theta term is showing. You are saying that the grid, that a three-dimensional grid, you are considering the whole space. So here actually the sine theta for the elevation and the azimuth angle. So in
Hmm.
that case, sir, this there is two matrix you are doing the so this plot, the elevation versus the azimuth. Sir, these two plots, sir, can you explain the in terms of 3D modeling, that how we can think of?
Okay. So this is the staying vector again for one-dimensional case. I have not given for 2 dimensions. For 2 dimensions, you will have a, sorry, for 3 dimensions, you'll have this coordinate system, and uh, typically, so if you have a source here, okay, so what you want to find is azimuth and elevation. So this angle you can say is phi, the elevation with respect to the z, x, y, and if you look at the projection of this in space, then this angle is theta, the azimuth. So there are 2 angles here, right? So in 3D, azimuth and elevation. Of course, there is this r also, the distance, but that we cannot find using DOA methods. So direction estimation methods cannot find the distance very easily. It needs a lot more processing and other modeling. Is this the
So
3D model you were asking?
frequency and time estimation can model that, right, sir? The in this paper I saw on the angle, but sir, in previous lecture, sir, I saw on the time domain and frequency domain. Time domain means the this different frequency it is estimated, and time domain
Yeah,
means
yeah.
that
So
say multipath kind of problem.
yeah, true. So I am here only interested in direction estimation, but sparse methods can, equally well be used for finding other quantities such as sparse frequencies or time of arrival, or if you're doing channel estimation, where the peaks arrive, frequencies. Yeah, all of those you can use. So I'm focusing on one application. There are of course many other applications where compressive sensing framework is useful. That's what I mentioned in the beginning, right? So
Yes, sir.
the
So
framework is very useful because of its generality. So you can use it for any
yes, sir.
problem where there is sparsity. Yeah.
Yes, sir. So the grammatic still applies on those. Can be applied on those grammatics.
Gram matrix, yeah. So gram matrix is more used in a DOA context, but there also it could be applicable. So yeah,
Okay,
it's
sir.
yeah.
Thank you, sir.
Sir,
Yeah.
sir, sir, in this model x equal to s plus n, sir, s you have taken any real number, sir, or e power j omega n? Sir, a we know
Hmm.
because these vectors. Sir, s, sir, is any real number or e power just e power j omega n, just s?
S, 1 minute. I don't have S. In the previous slides, maybe.
Sir, n way is Gaussian distribution, sir. S, we don't.
X, you mean? I don't know.
Sir, x equal to a plus n model now, sir. A is the vector steering vectors and s is the
Huh.
signal now, sir. So, what will
Okay.
be s, sir, generally? Generally, sir.
So S in this S1, S2, this thing?
No, sir. No. X
No,
equal
okay.
to y equal to hx plus n model, no, sir.
So Y
Yes,
equal
sir.
to AX plus N. Yeah.
Ax plus t,
Huh.
xt, sir. What will be xt, sir? Generally, it will be any real number or
It could be anything,
okay,
complex or real. For me, it is
complex or real.
complex. And yeah, all this processing assumes complex.
Means
Because you
e power
see,
j.
my prior covariance assumes complex Gaussian. So X is complex.
Okay, okay, sir.
It depends on the application. So it may be real, it
Depends.
may be complex.
Okay, sir. Thank you.
Excuse me.
Yeah.
In coprime or and nested array, we have taken only the two numbers, in the sense 3 and 5 or 4 and 6, something like that. If we say take 4 or 3 things, can we able to take it in that way, or how? Which one will be better?
You can have more levels. So to say, so for example, I have two levels. So nested array has two levels here. You can say one dense and one sparse. But you can have on top of this, you can have another level of nesting, or you can have multi-dimensional co-prime arrays as well. So people do that. That's also possible. Only thing is they may not be very practical because the arrays become very huge, and these things. All these things work under the assumption that there is some stationarity of the signal across space. What we are doing is we are taking a ULA. We are saying it's not required, not good enough. I will spread out the sensors and make it sparse. Uh, but that works in even that kind of works in certain assumptions as well. So one of the assumptions is that even if you go very far away, the stationarity assumption of the signal is still there. You're still receiving the same signal. It's not something else or noisy, right? So those assumptions may start to deviate. So hence, higher level of nesting or much larger arrays may not be very practical.
Okay. Okay.
Okay.
Thank you.
Sir, which reference shows the this prime number, or sir, this any reference shows this co-prime this collinear co-primary?
Yeah. So this is the end. So the first two references, right? So they are about coprime and nested arrays. So
Thank you, sir.
that's where they were introduced. Yeah. Okay. Any other questions?
Sir, I have one idea that, sir,
Hmm.
if the augmentation on the differentiating, sir, if we do some bootstrap method to generate the sample, so sir, it will be more random and kind of taking more sample on the input space.
So random
Bootstrap method,
sensor
sir.
locations,
Yes,
you
sir.
mean?
Yes, sir. Yes, sir. Bootstrap method kind of where the making a more plausible solution on the
Hmm.
same set of array.
So random arrays also people do use, but I think that um, that may not have same properties as sparse arrays, because sparse arrays are very structured. They use very specific structures. So random arrays, uh, yeah, one has to look further into this, but how much of properties of sparse arrays they carry, it's not clear to me.
Okay, sir. Sir, if the covariance, the MC covariance matrix is structured, so sir, instead of SBL, I know one algorithm which called structured group sparsity. So I forgot the name, sir, but they use some graphical tool set to define the structure in the matrix. So
Hmm.
sir, sir, that I want to say. Thank you, sir.
Yeah. So if you have additional structure in your problem, or you know that somehow there are multiple DOAs present in one region, so then you can group them and all. So all that additional structure you can easily incorporate within the SBL framework. So, and people have done that also. Like some of those are already people have tried it. So that is possible. Yeah.
Thank you, sir.
Okay. Okay. Any other questions?
Sir, when I seeing your introduction, sir, in that time, sir, I though it is out of this scope of this FDP program, if Kishore sir allow me to, I can speak for different topics. Just a single question on Monte Carlo filtering.
Okay.
Yes, please go ahead, sir. Actually, we are planning for a validity at 1:30. So if it is precise and concise, then we can go ahead, sir.
Thank you, sir. So the Monte Carlo filtering has advantage. The EK, the extended carbon filtering, have more advantage on this particle filter or Monte Carlo filter. Sir, if the any new update on this particle filter have been done to get more better solution than a traditional particle filter?
Uh, Particle filters. So one of the recent work people are doing is called particle flow filters. So they're not exactly particle filters. So but they use uh, differential equations to model going from prior probability to posterior probability, and instead of doing weight update, what they do is they migrate particles using some particle flow dynamics they devise, and flow the particles from one density to the other rather than giving them different weights. So this way you need fewer particles, and computationally it is better. So that is one thing, one of the novel new things people are working on. So it's called particle flow filters.
Okay, sir. Thank you so much, sir.
Okay.
So if no queries from the participants, then we will take a 5 minutes break. With the permission of the expert speaker, I would like to conclude, sir, if you permit. Sir.
Sure. Yeah. So yeah, I don't have anything else. So if there are no questions, we can stop.
Thank you so much for accepting this invitation and delivering 2 sessions, 4 hours long duration expert talk, sir. We were very thankful to you, even the department of TC and NIIT Andhra Pradesh. And I personally thank to you, sir, for accepting this invitation. In future, if any such workshops we are trying to organize, we may approach you to. We may approach you, sir. We request you to kindly accept our invitation, especially if any that comes from our department side, sir.
Okay.
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 Thank you so much, sir. As a token of appreciation, I request all the participants to give a big round of applause to the expert speaker. Thank you, sir. Thank you so much, sir.
Thank you.
I came to know that RVH Prasad has some query. Raising the hand. Any query?
Sure.
RVH Prasad, yeah.
No, sir. No, sir. It just missed.
Okay, fine. Thank you so much, sir. Thank you so much.
Okay, then, yeah. Bye, everyone.
I'll contact you later on, sir.
Okay.
Okay, thanks.